Cool. So now we're going to go in and start to implement some of these rigid body, these bounding box ideas for collision detection that we've been chatting about in the last few lectures. So I'm going to be starting off of the repo C17. There's a project called RigidBody 0.0, and this is built on a lot of Alberto's code. And I'll be kind of going through and talking a little bit about how to implement bounding sphere and how to implement a axis-aligned bounding box, and then also kind of going into how do we determine, how do we reorient it, how do we create out of a ARBB, or a realigned bounding box. And you'll find in the repo there's a couple of different projects that step through the progression of this, and so I'm not entirely certain at this moment whether or not I'll go through those or I'll just kind of do things ad hoc. But either way, you can find this code in the repository with the outcome in SAT and the entity projects later on. So let's kind of jump in. As we see here, we have the project open in the app class.cpp to kind of go through what's going on. In the init variables, we're creating a creeper model. In this case, let's set up the creeper. You'll see there's a bunch of different ones, options kind of commented out, so you can sort of choose which one you'd like. There's also a Steve model, which we'll use later to detect collision. And down here, we're just taking that model and then rendering it by adding it to our render list, and also the respective rigid body, which we'll talk about in just a minute. So let's just see what that looks like. If I hit compile and run, we'll see here it is. There's not much there. We can move the camera around with the arrow keys. We can also use the middle mouse key to rotate the creeper around. But you can see there's nothing in there at the moment. So let's take a look at this new thing here, which is this MP Creeper RB My Rigid Body. So there's a new class that's being added here, Rigid Body. And you can see the Rigid Body class has already been defined here. We have a mesh manager. This is so that we can render objects to the scene so we can visualize our rigid body. And I'll talk about what a rigid body means in the context of this code example, and whether or not it's visible, which we're going to set to true, and all these variables that may look familiar to you if you watch the lectures, right? The radius, so imagine a bounding sphere radius, our center point, what's the center point of our object and how do we calculate that, our minimum coordinate and our maximum coordinate locally, and then our maximum and minimum coordinate globally, although this should be changed to global. And then also what we call the half width and the model matrix that would then take us from the local to the world coordinate, which in general is your model matrix for your object, which we'll talk about how to set that as well. And a variety of different functions that we haven't implemented yet. Cool. So first off, let's go into the implementation here to the rigid body CPP, and we can see that the initialization initializes everything to just sort of white and 0 and identity, and then let's go down to our initialization function. So init is what we use to initialize by the point list. And what is that? Well, look, if you look here, you see when we create the creeper rigid body, we pass to it a vertex list, and that's exactly what this vector3 point list is. It's just a vector of vector 3s. And so you can use that to figure out data, the bounding volume information based on the actual data of your vertices, which we'll see in just a minute. And then a couple other kind of things, and then here, add to render list, this function would allow us to add objects. Let's say I wanted to add a torus, and we can do that with our M4 world, our, let's do color white, and then render solid. Maybe let's make this red. oops, you'll notice that in app class down here, we add the rigid body to the render list, and that's what calls this, and then that'll call the mesh manager and add it. So with a little bit of luck, if we run this, you'll notice now there's a torus in the space of the creeper. And you'll notice the creeper being oriented around 0, where the head is actually away from 0. The midpoint's not set correctly, and that's for a good reason. The 0 point of the creeper is actually not at 0, not in the middle of the model. So when we rotate it, notice the rotation of the torus is not being aligned to the object. And so that's the first thing we want to fix. So let's see here. What we want to do is we have this function here, set model matrix. And what we want then is an app class. When we set the when we update, we want to also update the model matrix, set the model matrix of the creeper to the model matrix of the creeper. And you'll notice that this already is kind of here for us. Oops, it's right here actually. Set the model matrix to the rotation matrix. Well, we need to do that also for the rigid body, which is not being done. And so what we need to do is mp creeper RB set model matrix to the creeper get model matrix. No, that's not what we want. Apparently, let's see. That's not what we want. We want, let's do the following. We can go matrix for m creeper equals to this. We'll move this here, and then that way we can use that. And now, when we rotate the creeper, we're also rotating the torus. And I believe this code also has code to move the object around in X, Y, and Z. And you'll notice now that the translation also follows. I want to kind of point out really quickly that this extra object we're adding, the object inside of RigidBody, is entirely what's called a reference geometry. Meaning it's geometry for your reference, for debugging, for visualizing what's happening. All of the rigid body collisions, collision detection stuff, resolution is math. It happens behind the scenes. It doesn't happen visually in any way. It has visual outcomes, right? When an object bounces off another object, you see these things bounce. But in a video game, you never see a bounding box that then highlights, and you know what I mean? So just keep in mind that a lot of this stuff is there for you, so don't be shy about doing things differently if you feel the need to do so. In fact, a lot of engines will use the geometry shader to generate reference geometry, so you don't have to do a lot of that stuff in the engine. But that's just kind of an aside here. So cool. So now we have a nice little thing. We probably don't want a torus. We want to have, first we want to have a sphere, right? And then we also want to have, and let's make the sphere, we want to do render wire, and let's make it white. actually, yep. And then we want to make a box as well. Let's do a wire cube, and we also want to, we'll make that yellow. And let's make also add wire sphere. Great. Let's only play with the sphere initially. And so, boom. Cool, now we've got a sphere. You'll notice that the sphere isn't exactly correct for this object. Although at least it'll rotate it with it, and that's nice. Now we have a sphere. It's pretty useful. The other thing we want to do is this creeper model is a little bit hard. Like it kind of looks like a box. I think it is pretty much a box. So let's do something a little bit more easy to understand and visualize. And I think that the sphere cube model here is just that. It's an object with a small cube on top and a sphere on the bottom. And you can kind of see here, there it is. It's a pretty useful little object to kind of visualize how we're going to encapsulate it in a bounding volume of some kind. And so to start off, what we want to do is we have this sphere that is, you know, trying to contain the entirety of the model. And so how do we do that? How do we determine what that is? Well, we have this function here, the big 3, or I'm not sure what that stands for, but here we can go through our point list and figure out, okay, well, what's our maximum point, what's our minimum point, and we're going to do that locally. So we have this function, this value here, the minimum local and the maximum local. And so let's go mv3 min local is going to be equal to mv3 min, max local, which is going to be to the point list 0. And then we're going to go well, let's do this vector 3 point in the point list. Great. So now we're going to go through each point in the point list, and we're going to try to figure out the max and min and the minimum point of everything. And so let's do that. So it's very kind of straightforward. And it's kind of like verbose. We're going to do this for every axis independently. It's not like we're going to check each point against every other point, because we want to see what the maximum displacement is in x and y and z, not necessarily what's the point that's farthest out from the center. Although it's not entirely true. In some cases we do want the maximum point from the center. That would give us the minimum sphere. But let's kind of explore this first. So let's go if the mv3 min l dot x is, well, actually, I want to maybe put this, let's stick to a set of conventions. If the thing that we're comparing to is less than this minimum, then mv3 min l dot x is equal to that thing. If it's greater than the maximum, then the maximum is going to be equal to that thing. And now we've got one already for both min and max on x. And now we do y and z. And so y. Be really careful when you write this kind of code, because it's super easy to make a cut and paste error. And you'll be debugging your code for 5 hours and won't know why. And it's just because one of these is not what you thought it was. So it's often a good idea when doing this kind of code to read through it line by line. So if x is, if the x is less than the minimum x, then the minimum x is equal to that. If it's greater than the maximum x, then max is set to that. If y is less than the minimum y, it's set to that. If y is greater than the maximum x, then we set the max to that. And if z is less than the minimum z, then we set the minimum z to that. And if the z is greater than the maximum z, then we set the z to that. Great. And now at this point, let's do a quick little breakpoint here and see what we get. And just inspect those values and see what we kind of expect to see. Oop. Well, it doesn't look like we're actually getting this code to hit, which is confusing. Why is that? So let's go to this and go and debug in there. And init is hitting the void, but it's not hitting this one for some reason. And I think that's quite strange, isn't it? Okay. Where's my constructor? My constructor is here. I want to go to the definition of that constructor. Do I not have a constructor defined? Mayhem! So yeah, there's no constructor defined apparently, which is on me. Great. You'd think that would throw an error, but it didn't. So that's fine. So what we're going to do is we're going to call init on this a point list. Oops, wrong file. Okay. And just make sure that, no, here we go. No, this is I'm in the constructor. Why did it get mad at me? Okay. Okay, why is it not going into our constructor? Well, I'm in release, so one good thing is to not debug in release mode. You want to debug in debug mode, because sometimes your compiler will skip things and do things that are unexpected. It's a lot harder to debug, so that's most likely why. Okay, now let's do it. Great. Okay, there we go. So now we're in the code. So we were writing the code, it just wasn't being very nice to me. Okay, I'm going to run to this next breakpoint. So now we expect our minimum to be, if we're looking at our image, we have a small, like a ball down here and a box up here, and so we kind of expect a very big Y in the maximum and a very small y in the minimum. So the minimum is looking like the minimum L, the minimum point is -1, so that's what we kind of expected, and the maximum we expect a big Y, the max Y is 4.9. So that's kind of right. So we do, what it looks like now is we do have the correct minimum and maximum points. And so now we want to kind of determine what's the radius of the ball of a sphere that would contain the whole thing. And one thing we can do, so instead of doing, there's a couple of ways we can approach this, but let's take kind of the more pedantic way. And so we can actually go through the point list again. Well, first we have to actually determine what the center point is of this object, because we want to know what's the maximum point from the center of this thing. So how do we figure it out? And that's where we bring in our center, right? To determine the center, we can effectively just sort of take the minimum point and the maximum point and sort of find that midpoint, right? So one way to do that is to take the MV3 max local minus the MV3 min local, right? Multiply it by half, and then add it to our min point. So if you kind of think about it, we take our maximum and our min, we subtract them, we get a vector, and then we divide that vector by half and we add it to the minimum. That's going to give us our center point. And as a gut check, we know that our negative y is -1 and we know our maximum y is 5-ish. So what we expect the midpoint to be is 3 plus -1, which is 2. So let's see what we get. If the center point, our min y, our y value right here, it looks correct. It looks like about 2, which is what we expect, which is great. Now, one thing that's kind of interesting here, maybe we want to kind of take a look at this. Generally speaking, with a object that is centered about 0, you kind of want to see an x and a z that's close to 0, and we look at this big number here. Well, that big number is actually e to the -0.07, which means like to a very, very small number. And this is what I would call truncation error in many cases. So it's up to you how pedantic you want to be in this stuff, where you could, in theory, compare things and kind of clamp them to epsilons. Epsilons can be like 0.0001, and anything below that is considered error in your engine. But we're not going to do that, but that's just kind of a hint. If you want to make these systems a little bit more predictable or more deterministic, which is going to be a thing you're going to fight forever if you're working at this level, epsilons are your friend. So cool. So now we have a center point, and using the center point, again, we can use the same code, and we can go through each point and determine its magnitude. And so we're going to use a little float. Well, actually, we don't even need to do that, right? We have our radius, and we're going to set it to 0.0f, and we're going to say if the point, the GLM magnitude, is that a value? Is that a thing? Okay, let's do this. If the if point minus the MV3 center length, is that a thing? Are we allowed to do that? No, that's not the length we want. We want like a GLM magnitude. Is there like a function that does that? Distance, maybe. Great. Distance. Why is it not happy? Ah, okay. So actually, GLM does the work for us. We don't have to subtract them. But if the distance is greater than the radius, then the radius is equal to this distance. There's actually kind of a fun trick you can do. Float temp. If you ever really care to do something like this, it's kind of a fun little C++ trick. That way you don't have to do the calculation twice, right? But now we can determine our maximum radius, right? So let's check here what our code is. And that in a thing I do, it's just a nice place to put a breakpoint. It's really irrelevant what the line of code is, but you can do whatever you want. The thing is, you can't really break on a curly brace. So now let's take a look at our radius, and our radius looks about right. It's like 2.9, which is what we expected, right? So cool. Now if we apply, now we want to take that radius. Now it's a variable that we can use here, and we can set the radius of our sphere by that size. So this sphere is going to be a unit 1 radius, right? So we want to do a GLM scale of this by a vector 3 of m float m radius, which I think should work. Cool. Now, this doesn't look right. I mean, it sort of like seems correct in that it seems to be the right size. Like if you imagine that sphere and we moved it up to be at that in the middle between those two objects, it should contain the two. So we kind of need to move that bounding sphere. Right now we're scaling it to the right size, but we also need to translate it. We need to translate this by what? Okay, I'll pause, I'll let you think about it. What are we moving it by? We're moving it by the center of this object. And then now we should have, oops, it's a little bit too much, huh? Apparently not. Apparently we need to maybe, I think I'm doing this wrong. I think we're translating as scaled, and so we need to unscale the vector, which is not correct. So let's do the translation first. We're going to translate, then scale it. Great. Cool. So this looks right, almost. You know, but something kind of is off. Like, what is off here? Well, if you look at, and let's try to do orthographic here. If you kind of look here, it looks like this line, these points of this cube are outside of the sphere. And you're like, wait a minute, didn't we calculate the maximum thing? Well, this is where you have to kind of consider the nonlinearity of a sphere and how it isn't perfectly described by a mesh. This is a straight line, but a real sphere would actually have a curved surface here. And so the math turns out that you can imagine, like, if these 2 points are on a sphere, the point in the middle is not going to be on that line. It's going to be out of it. And if you map it, it's approximately here, and you have this sort of curve. So those points of the cube actually are contained in this sphere. It's just the geometry of this generated sphere that we have here doesn't represent that. So if you would increase the number of vertices and the amount of data in the sphere, you would eventually converge on that. Similarly, down here you have that same example where you can see the sphere sort of intersecting out, but you can kind of see with the sphere, like in this particular example, it's very, very easy to see that that curve would contain this thing. So yeah, that's sort of something, kind of a gotcha that you have to kind of keep in mind. Now, you can see this bit, this is actually quite expensive to calculate. The reason is that this line of code, the distance, requires a square root. And computers are not terribly good at square roots, like you can do it better on a GPU than you can on a CPU, but we're on the CPU side, and the square root is going to cost you. So there's a couple of ways to deal with this. So one way is, actually we're going to create a second value here. We're going to call it mfradius2. And mfradius2 is going to be the squared radius. And so what we're going to do is we're going to use a different function called distance2. Distance2. And distance2, the difference between distance2 and distance1 is that it doesn't do the square root. So if you know the Pythagorean theorem, the magnitude of a line is like x squared plus y squared and the square root of that. But if you don't take the square root, then you just have x squared plus y squared. And those values are guaranteed to be positive because they're both squares and they're a sum of squares which are positive, and the sum of positive numbers is also going to be positive. And the reason that's really good for us is that then we can basically calculate against this mfradius2 value, which I don't know why it's highlighting it and giving me an error, because whatever. And then we're going to compare it against mfradius2, and if mfradius2 is whatever, then we set it, and now we have a really nice way to alleviate the need for the square root, which is a very expensive operation. This is actually something to keep in mind when you're doing boundary checking and things like that as well, and which we'll use later. And then if we do mfradius2, and then we can basically go and say, okay, well, the radius is going to be mfradius2, the square root of that. Cool. I'm not sure why I'm getting a what looks like an error there. But we'll see. It'll probably build because there's nothing wrong with that line of code. Undefined. You're undefined. Anyways. And you can see we have the same result. But the code is a lot faster. Significantly faster, in fact. So that's nice. It's pretty good. However, we can kind of do this even faster than that, which is going to be just, well, we know what our center point is, right? And we know the maximum and the minimum points. So what if we determine this new variable, we actually have it already defined, called our half width, or also known as the half vector. And the half width, actually we're going to use it to determine the center point. We're just, the half width is literally this value right here. It's the maximum minus the minimum divided by 2. That's our half width. You can imagine a center point can be calculated off of this half width. Because if we have our minimum point, we can get to the center from that. Just like if we wanted to get our minimum point, we would take our center and subtract the half width from it. And so now we've got this nice little thing. And so we can not even do any of this stuff. And then we can say mf radius is equal to the magnitude of the half width. Not sure how to do the magnitude. Okay. Length. Cool. Now, if we do this code, if we do it this way, you'll notice something kind of funky happens. There's a bit of error, right? There's a bit of space and padding that wasn't there before. We don't have a perfect fit. And that's because if you take a line and you find the max, if you took a square and you found the maximum width and the maximum height, the maximum width and the maximum height create a vector that, if you think about the square on the top, is going to extend to the right of the square a pretty good amount, right? If you had to draw a square inside of this that contained both objects and then drew a circle around that. Now, there's a reason why we want this, because we want our circle, we want our bounding sphere to be an early pre-test for the underlying geometry. And so this is okay. This is actually something that we want, because we're not going to test collision against the sphere ultimately. We're going to use the sphere to determine whether or not we want to check a more accurate collision between the objects. But you can kind of see how by using the maximum point and the minimum point and then the half width, we don't get a perfect fit. There's a little bit of padding that we get as a result of this. So we're going to keep it that way. This is a pretty cheap way to do it. We still want this MF radius too, by the way, which we'll now just calculate as the radius times itself, which is fine. I'm not sure why this keeps giving me that error, but that's Visual Studio's problem. And cool. So now we've got a bounding sphere that contains this object, and if we were to move it around, represent, very well these two objects and contain them, which is pretty cool, pretty nice. So now we actually have this bounding sphere around this object. Let's move back to our previous model. Instead of using this sphere cube thing, let's use our creeper guy and see what that looks like. Great. Oops. And now you can see that because the nature of the this creeper is that bounding box in a way, it's effectively a box. It fits quite perfectly in there. There's not too much sort of left to the imagination. Let's now add another model. And we're going to add Steve in. Steve is also from Minecraft, right? And we're going to translate Steve to put him at 2.25 or whatever. We're going to set the model matrix, and we're also going to create this rigid body for Steve and set that respectively, and let's see what we get. It's not going to render because we need to add Steve to the render list as well. Cool. So now we've got these two objects that are pretty well contained, and you can see how this code immediately worked for whatever, because we're going point by point in the thing. Now if we move these two into collision, nothing happens. Why does nothing happen? Well, because we're not making anything happen. And so as we talked about in the lecture, the bounding sphere test, the collision test, is about as easy as it gets. We already have this function defined here for us, which is colliding. And let's see, it's not defined. It's not actually, there is no code, so let's create it. Oh, well, actually there is code, it's right here. And you can see the definition of this function. It is colliding, and it takes another rigid body as an input. And so let's go ahead and use that function. And we have here, let's set the color to white, and then let's change this here to the color just so that we pick that up. And if we do this, if MP creeper RB is colliding with MP Steve RB, then we want to set them to a different color. Otherwise, let's set them to white. So right now, this should always be false. Is colliding should always hit false, because there's no code in there. Great. So what we want to do now is we want to determine if the two centers are touching, are closer than the radiuses of the respective rigid bodies. And so all we have to do is basically, if our local center minus the other's center, right? Actually, we just do GLM distance of these two is less than our radius plus the other's radius return true. That's it. Or is it? Because it's always going to be red. What's going on? Well, the center does not take into consideration the model, the model matrix, the translation, the displacement, the rotation, all of that stuff. So we need to think about that. This center is not the center of our object. It's of the actual object in world space. It's the center of our object in its own space. It's like its pivot point, if you want to think about it that way. And so we actually need to create almost, well, what we can do is we can create a new, well, we already have it. Here we go. Get center global. This function's right here. And all it does is it takes the center and multiplies it by the model transformation of that specific thing. And so we can get center global there, and get center, oops. All right, and then get center global there. And now they're not, and when they get close, they do line up. You can see there's actually a situation where, like I was saying before, the nonlinearity of the sphere kind of gets in our way. Where you can see from the top, they're clearly touching, but from the side, because of the way it works, there's a sort of overlap that's not clear. But if you were to draw an actual circle there, they would clearly be touching one another. So that's it, right? Now we've got a very basic collision test. In fact, we can even do this with rotations. So if I rotate, if I can figure this out, you know, I can like rotate it like that, and bring them into touching each other. I can move them. Bounding spheres are really, really robust tests. So to make this a little bit more optimal, you can see this function, it's funny, right? Here, this code only happens once. When you initialize the bounding sphere, this only happens once whenever you do it and as often as you change the geometry underlying. But that doesn't happen as often as is colliding. Is colliding is running every single frame. So this is the most high performance code you need to write. So there's a few things we can do. First of all, we can return this here. We don't need to create an if. We don't need to branch. That's going to speed it up. Another thing we can do is, instead of get center global, what we can do is here we can create let's create a center. Well, we have a center global variable here. So what we can do is simply set mCenter global equal to get center global after we've set the model matrix. Great. And then we can use this instead of calling a function. The reason calling a function, by the way, it's more expensive, right? And another thing we can do is we can inline the is colliding code. twice. Oops. And so inlining will, instead of creating a function call in the code base, it'll actually like cut and paste that code. Oh, we got some errors. MV3 center G is undefined. But there it is. Oh, it's defined in a different place. Clearly in a different, because we have so many versions of this code. So let me do this. Okay, great. So now it should be defined. This is why Visual Studio is getting confused, because there's a lot of similar function names and a lot of similar classes and such. Still crashing. Unresolved is colliding. Because, well, no, it's right here. Part 0. Okay. Yeah, inlining, you sort of need to know where to put the inline, I think, which I never do. Okay. What's going on? Why can it not find our code? Maybe let's clean and rebuild, just in case. And let's see here, is colliding, is it calling the correct thing? You know what, I'm just gonna get rid of this inline first. Let's get it to build. There we go. Inlining can be a little bit temperamental at times. So now at least we can confirm that our code still works. We're using global, we're avoiding a branch, and so the performance is better, although unperceivable. But if you were to scale this up to thousands of objects, you would notice it pretty significantly. Another thing we can do is, we talked about the radius 2 earlier, so we can do the distance 2 function here and instead operate on the squares instead of the square root. And that's going to let us also avoid the square root every single frame. And this is a pretty huge performance impact, even more so than everything else we just did. So you'll notice that there's an error. It doesn't seem to work quite correctly. So we need to figure out what's wrong here. And that might be because, why could that be? Question is, I'm not even sure if this distance 2 function is what I think it is. Okay. Well, let's just do the math ourselves. Instead of calling this function, we can say return MV3 center G times X times MV3 center G times X plus Y plus Y plus Z plus C. And you'll see me doing this actually pretty often, where, okay, and now we're going to do this for the other. Return if this is less than cool. And you can kind of see what I mean in that now we don't have to do the square root. We're just squaring each component and adding the square of each component of the other one, then we're determining if it's less than the other. And I'm going to have screwed something up. There we go. And this should not work apparently. Okay. What am I doing wrong exactly? X, X, Y, Y, Z, Z, radius, radius, let me pause this really quickly and figure out the issue. Alright, so I found the issue. The issue is actually one I've never really thought about before, and I think it's a valid one to kind of point out. The distance approximation by using the squares is not actually linear across all values. Let's see what happens and why this is taking place, because I think this is really cool. I've never really seen this before, and I've never really thought about it before. So as you can see, there should be a collision here, but there isn't. It's only when we get to this point that it happens. And it doesn't seem to, it seems like half, but that's not really what's going on. So let's take a look at the error, the null, the false negative here. And if we go to the code and I kind of broke out everything into individual steps, and you can see what's going on very, very clearly. We take the difference, we get a vector, we get the length 2, which is the distance squared of that. And we see that that distance is 2.43. So, okay. And now we look at the MF radius of 2, which is 0.8, and there's one of our hints. And then the MF radius 2, which is 1.3. And the rad sum is 2.1. And the length is clearly bigger than the sum. So what happened here? And why are we getting a failure? Well, the hint is here. Our second radius, our radius squared here is under 1. It's a value of less than 1, which means that a value less than 1 to the power of 2 is going to be a value less than 1 that is lesser than itself. And so we start to see nonlinearity when one of the radiuses or these distances start to go underneath the value of 1. And so we can't really do this for all cases, and we really shouldn't do that here if the radius is going to be less than some amount. So that's sort of kind of a wacky thing. So for the time being, just don't use this unless you really want to create that hierarchical system, and let's stick to the simple and optimized version that we can think of. There are other ways to sort of estimate these distance functions to speed things up, but in practice you're going to get a much better speed up by choosing when you do these checks versus trying to optimize everything down super well. So if you can control your situation, you can make sure that things have a radius over 1, you can make sure that calculations make sense, then you can avoid a lot of these problems, and you can still use those optimizations. Cool, so let's move on to, now we have this, and can we now introduce a bounding box as well? So like we had before, let's add the cube to our list, And let's sort of just kind of not really think too much about it and scale things up the way we did for the sphere. Oh, actually, now we don't want to scale up the cube by the radius. We want to scale it up by our half vector, or actually twice the half vector, because if we do the half vector, it's going to be half that size. Because from our point right now, like if we don't do anything, if we don't scale it, we just translate it, for example, what we'll see is we'll see a little cube, but it won't be the correct size. So as you can see here, it's a little bit hard maybe to visualize. You can see there's a yellow cube inside, but it's not scaled to the appropriate bounds. It's wider than it should be, and it's not as tall as it should be. And so what we need to do is we need to scale it, scale it like we did before, and we actually have that half vector already calculated. So let's see what happens when we just do it in this way. Great, that looks cool, but it's a bit small, isn't it? And that's because we only scale it up by the half vector. So we actually do need to multiply this by 2. And now you can see, in the case of the creeper, we've got an almost perfect fitting bounding box. It's better to look at orthographically, but you can see it's almost perfectly fitting. In the case of Steve, the other character, you can see these fit almost perfectly inside of the sphere and bound the model almost perfectly. So now you can imagine if we wanted to rotate, and we can use somehow, like here you can see the two are a bit not really touching, but the spheres are clearly colliding. So we determine a collision, but it's not really accurate because these boxes are not actually touching each other. So how can we do something about that? And for the next section, where I'm actually going to be using the arrow keys to move things around. So what we want to do is we want to change the collision function to use this as a pretest. So instead of returning verbatim, we do if this is true, then check bounding boxes, else we return false. And here we're assuming in some point we return true. In fact, we don't really need to do the else. We can just return false when things don't work out. And now we want to do some kind of check the bounds of the box somehow. And again, we're going to see a very similar pattern to before, where we want to see if the minimum global location and the maximum global location of the box is going to be sort of equal to, is lesser than the max, and we're going to do these sort of tests per sort of boundary checking and min-max of everything. We'll be able to determine that they're overlapping. And so let's do that. Where, okay, let's do it. So one thing we can do is if the if RMV3 min G, and we have to kind of pay attention to min G here because we don't actually set it to the world location anywhere, so we probably want to update that somewhere. And the best place to do it is here, the same place we did it for the center. So we want to do min G is going to be equal to, and you can see what we did up here, we're just going to copy this code, our vector of M4 to world times vector of M v3 center. Instead we're going to do, instead of v3 center, we're going to do MV3 min L. And then repeat this for the max. And now every time you set your model matrix for the rigid body, you're going to also set these global, the world space locations as well that we can then use in this function. So if min G well, let's do this. If the maximum x is, let's see here, we're max and min. Well, what we want to do is we want to make sure that the this is always my favorite code to write. If this is less than the mv3 min g dot x, then there's no way they're touching. And this is the other. Then return false. If the mv3 max g min g dot x is greater than the other mv3 max g dot x, then return false. And then we repeat this for, we can do else. It's not really necessary, but let's do it for each axis. So now we're going to do y, and I probably wrote this incorrectly, but we'll find out in a minute. And if none of these, so we're basically trying to get an early out. So if the min x is less than the max x, then there's no way they're touching, because if our minimum, if our maximum point is less than their minimum x, there's a line in between, right? There's no way they're touching. If our minimum x is greater than their maximum x, there's a line between them. And same thing for the other axes. So let's see now. Now you'll notice, if I did this right, let's go into orthographic here. Now they're not touching, right? But when the bounding boxes overlap, you can see that the collision does get registered until it doesn't on the other side, or if we go down. And this is actually the separation axis theorem in action, but in a very simple way, which is, well, right here you can kind of see my maximum of the maximum point of the creeper is less than the minimum point of Steve. If I took these two objects and I sort of squished them down to a line on the bottom, and you know, just like their shadow, if you think about it that way, there would be a gap between their shadows. And if there's a gap between their shadows in any axis, then they're not touching, right? If I can draw a line, or what's called a separating axis between them, then there's not a chance that they're colliding. Now, this presents sort of an issue where these are not touching now, but if I start to rotate the creeper, you'll notice, hey, wait a minute, it's clearly touching here. If I look from the top, you can see the two are touching, right? But it's not registering a collision, and that's because we're dealing with an oriented bounding box, and you'll see that sometimes it will touch, but that's only because we move that center point sufficiently where if we were to draw that bounding box oriented with the axes the way that it actually is, then there would be a collision there. But you can see that even though it's touching in this scenario, there's no collision. In fact, the best way to replicate this is by doing this kind of thing, where it's rotated into this way so that you can see the opposite direction, because we've actually moved the oriented bounding box to the left. So this is a limitation of AABBs, and one of the things that we haven't really done here is reorient the bounding box to the correct plane. So this is the next bit that we're going to do now. Is set up the axis realigned bounding boxes, and let's do that. So here we have now a test that checks if our spheres are colliding, and then we check the bounds of our box. And the thing is, though, we need to have a sort of third box. Let's make this one green or orange. Great. And now the orange is going to be equal to a new half width, the half width of the realigned. Great. And let's go and define that. And so I'm going a bit off script here. The later projects in the repo do this as well for you. HV of realigned. And what I want to do, I want to be able to calculate the realigned HV. So when I do this now, I'm just going to get an orange thing in kind of the middle. That doesn't really make any sense. It'll be in like the correct location maybe, but it won't give us much else. Or apparently it won't give us anything because this is a vector of 0. So it'll scale to nothing. So let's fix that. Now you can see it's just an orange 1 cube. Great. So what we want is we want to, when we set the model matrix, right, we now have a HV plus a model matrix that we can then determine the new realigned bounding box. So how do we do that? Okay. Well, I'm going to do this a little bit brute force. There are more eloquent ways to do this, but I'm going to go through each point of the the box, and then sort of determine the max and min of the box. So first I'm going to do float. Well, I'm just going to create a vector 3. V3 max equals well, vector 3 0 min vector 3 0, and then for each permutation, what's the best way to do this? So the first thing I want to do is I want to reorient my half vector. So my new half vector is simply going to be my MV3 half width. With realigned is simply going to be really just this. Well, okay, here's the trick. The trick, I want to take the world matrix, and I don't want the 4x4, I only want the 3x3. If you recall the way that the translation transformation works, I want my translation matrix to be effectively the 4x4. It's in that fourth column. So what I want is actually, I don't need to do the vector 3. I want to do a matrix 3 of a 4x4 matrix. And this will strip out those other two, and then I don't need to do this. I just transform this and now this is actually the new half-width realigned. So let's just see what happens with that. Is this enough? Right, we've now basically created this box, and another thing we need to do, by the way, is we don't need to rotate the box anymore by the rotation of the object. We just need to have it in the correct translation, the correct scale, but we don't need this M4 world. We don't need to translate anymore. Although we do need the transformations of the object underneath, or do we? So let's just actually play with this a little bit, and we want to go identity. Now you'll notice there's a couple of things that are wrong here. This one doesn't even have one. Oh, and actually, that's not true. We do need to translate it because this is representative of what we're doing. So let's just see what happens first, because otherwise it's going to be at 0. We'll fix things as we go. So now we can see we have initially a orange box that matches perfectly the yellow underneath. But as we rotate it, you'll notice that it's changing. The half vector is changing. And you can sort of see it's changing in weird and strange ways that are not really representative of what we want. So no, in short, the half vector rotated by whatever is not enough, because we're just going to create funky things, and that's not really what we need. And so this half vector realigned is in a way correct in that it rotates, at least, but it doesn't rotate the way we want. It doesn't rotate in a way that actually helps us figure out what our new bounding box is. So this is not really the right thing to use. We want to create a new vector here. In fact, I don't even want to do it this way. Let's keep this as let's just keep this code here. And so let's go point by point in the box, right? We have, using the half vector, a point that we define. And a box has 8 points. So let's go for int I equals 0, I is less than 8, I plus plus. And let's actually do it in a little bit more eloquent of a way, where we can use a enum box point. And we're going to call it top left. Well, let's do top left front, top right front, top left back, top right back, top, and then we just repeat. Oops, that's not what we want. Here, and then we'll just do this with bottom. Cool, and so now we can go box point I, and I is less than, is equal to TLF, right? And this is a fun trick I like to use, but you don't actually have to do it. Equals to int I plus 1 I know this is annoying, but this is C++ for you. Oops. Great. And so now we're going to go through each box point, and we're going to create a switch on that. Okay. And then we're going to have a vector3 box or point box is going to be equal to our center. Point. And we also have this sort of, we do need this vector. We need like a vector HV oriented. Great. And now we have the center point, and to determine the box that we want to use, the box point, sorry, vector3, we basically have to figure out which way we're adding, right? So this is a little bit about convention. So the easiest one will be the top right back. So let's start with the easiest one. Top right back is going to be point box plus VHV oriented, right? And our bottom left front is going to be our PT box minus VHV oriented. Great. So now we've got these two, right? And actually, we can kind of rinse and repeat for all of the top, and we'll see why in just a minute. Okay, but let's note that these are done. And the rest are still under construction. So the top left front, we want the top left, so we want the x to be negative. So what we want is we want a vector 3 of VHV oriented x, but this is negative, but everything else is the same. And you can actually see kind of what I'm going to do here. The top right front, oh, and also the z needs to be negative as well, because it's the front. So all the fronts have a negative z, all of the rights have a positive all the rights have a positive x, and the tops have a positive y. So in this case, we've got top, which is positive y, left, which is negative x, and then back, which is the positive x. And same thing in this case, but in when you're adding, you know, whatever. And then in the case of of negative, we need to kind of think about it opposite. Well, so the top bottom right front will have a positive. Well, what we can do here is we can actually just add, if you really want to think about this as this has negative everything. Right, and this has positive everything, if you want to kind of keep the nomenclature. And so in this case, all of our y's are negative because we're in the bottom. The front is going to have a negative z. So this one has a negative z. And then the left and the right, the left has a negative x and the right has a positive x. But we might have to, no, this should be right. So bottom left front, so left to the x, negative x, bottom, and then front is negative z, and back is positive z. Yep, this looks okay. Okay, and now we actually do that same check that we had here. Now if point, now we have to change all the names. If point box x is equal to v min dot x, then v min dot x is equal to point box v3. Let's do this really quickly. Point box, point box, point box, point box. As you can see, like, this kind of code, it's super rewarding, but it's also very, very nitpicky, and you have to be really careful about making small little mistakes, because they do happen. They happen to everyone. So my trick is always to just have a really clear convention, which I'm not really using here, but you can kind of see some hints at it. Something that I've noticed Alberto uses very similar conventions to what I use. And if you code in C++ long enough, you'll notice that a certain set of conventions tends to kind of dominate. Cool. So now we've got, hopefully, and let's just see what happens here. So to start, what we want to see initially, and I haven't used this any yet, so don't expect the orange box to do anything, but what I want to do is I want to do a sanity check. So in this case, I expect my minimum and maximum to be the same because there is no wackadoodle stuff I'm doing. I want to see the exact same maximum and minimum vector. So if I hit the breakpoint here, because this model matrix is being set every single time, what I want to see is that this maximum is equivalent to my maximum here. Well, not the G, but the local one. Where's my local one? Which is right here. So max here, I'm seeing a Z of 0, a X of 0, and a Y of 0.8. So that's looking concerning to me because I'm pretty sure my maximum here has other values, like 1.6 and 0.25. And 0.8 is not exactly what I wanted, right? So that's no good. Now keep in mind that my center also has 0, so it doesn't explain why my maximum x and my other values are not being, nothing's happening there. So let's take a quick look and run through of what's going on. So first of all, we want to make sure that my half width and my v orient are the same. So here we see 0.25, 0.81, 0.37, and the half width should be the same, 0.25, 0.81, 0.37. So just to, yep, that's correct. Now these are equal, and we're starting at TLF, which is 0. I's should be 0. And let's start off with the center. The center is at 0.812, which is correct. Now we want to see my point box is going to equal to negative x, negative to y, and to z. So my top left point should now be, it looks incorrect though, because my x is here, that my MV oriented should have given me a negative x. So something is going wrong with my calculation, and I will let you guys see where my bug is. I don't know if you can, the code's quite small. It's because I didn't actually set it to anything. There we go. Oops. There we go. Yeah, so you actually have to set the thing, you have to actually update values, otherwise they don't work. Cool. So now let's do it again. And at this point, let's speed up to here. And I want to see that my maximum point and my minimum are the same. So now I'm at x is 0.25, 162, 0.37. My max here is 0.25, 162, 0.37. Great. So that looks like at least something's going correct. And now I want to see if this is working to some degree. So what do we do now? Now we've got a new oriented half vector and a new maximum and minimum point. And so we kind of just have to replicate everything. We have the min L, max L, all that stuff, and we have this realigned. And so we just have to sort of do that. Let's call it R, R. I'm going to use a little trick here. I'm just going to copy the cool. So now we've got this thing, and we have to reproduce this code again. We already have we have to kind of recalculate the half width, although the half width we already have. So that we can actually just equals to this. No, that's not necessarily true, because our half width may no longer represent the true half width. Yeah, so again, we can basically just copy and paste everything here. And you can notice we may have a different center as well. Let me change this just to stick with our convention here. And then min R, half width R. And now we have an MV3 center R, M half width center. So we have basically all the same stuff. We have another bounding box that sort of sits on top of our existing bounding box. And so now let's try to apply it down in our thing here. And we're going to put this MV center R as well. And let's see what we get. And you'll notice one thing that will immediately happen. It won't look right because we didn't stop the rotation. And you have this wacky sort of translation as well, which is incorrect. So what we need to do is we need to get rid of the M4 identity, but we need to put in the identity here. All right, we're not quite there yet. So let's just get rid of everything except for, let's go back and simplify things just a little bit so that we don't have to keep an eye on everything else. Let's get rid of this for now, and let's also go back to our simpler object. Oh, this is going to crash. Don't crash. Okay. We have to keep this piece alive. Oh, and we also probably should not do this colliding check for now while we figure this out. And we probably also don't want to do this quite yet. Great. And also this. Oh, I see. Okay. That's fine. Great. So now you'll notice the orange is kind of in a weird place, which we don't really want. So that's the first thing we want to solve. We don't want to translate it alongside we don't want to apply the world transformation to it in the same way. We only want we want it to be axis aligned, right? So let's get rid of this. And now you'll notice it's still up there. And it's going to move around, which is also something we don't want. The center should be correct initially. So if something we're doing wrong with the MV3 center, so one thing we can do here is the center R should be equal to the so something we're doing here with the wrong half width. So the half width here, and we're using the oriented M4 world, which seems correct, but then we're going off the center and we're adding to it the HV oriented, and then oh, I see. We're not actually using the correct values in the half width R, which is not helping us. So that might just have been a bit of a bug. There we go. Okay, so now it's looking a little bit better. It's in the correct place, but you'll notice now it's changing, but not like the right way. So it looks like something we did is incorrect. But sometimes it does. If you notice here, you'll notice that the top seems to be in the correct place sometimes, but not all the times. So it seems like we maybe are looking at the wrong transformations. So I'm going to pause this while I debug this, because this is one of those things that takes a little while. If you're watching on Twitch, you'll be able to watch the full amount. But I'm just going to kind of quickly run through all the different pieces and make sure that each one is correct. Okay, so I found the issue, which is kind of an embarrassing one, so I figured I'd share it with you guys. I want to encourage you all to own up to embarrassing mistakes so other people can learn from them. It's definitely a good feeling to find issues. So when I did a refactor of my code, you'll notice that I didn't read that code out like I said I should have in the beginning. And let's read it out together. If the x is less than the maximum, we should set the maximum to x. That doesn't sound right. If x is greater than the minimum, we should set the minimum to x. That doesn't sound right. Looks like I flipped my definitions in my refactoring effort, and that's not correct. So these are backwards, which is why you saw some funky stuff. Should be min max, not max min. like I was saying, this stuff can be a bit temperamental, and you know, let's just say that the code is never wrong. Only you are, and that's a good thing. But yeah, otherwise it looks like max, max, min, min, min plus, all that stuff is good. I didn't test it, so we'll see. Maybe there's another bug, but hopefully it's a little bit better now. Looks a bit more reasonable, although one thing you want to see when you're doing this stuff is you want to see that yellow box completely encapsulated. You'll notice that there's some issue here. It looks like it is scaling, but kind of in a weird and strange way. So something's not being correctly encoded. And so let me pause again and find what the next issue is. Okay, so I think I actually led you guys astray. And this is not the right approach. You don't want to add the half vector that's rotated, because that's not necessarily, I'm not correctly deciding which point of the box to use, and this is a bit of a confusing point. I always mess up, actually. I've messed this up like 3 times. It's funny how I forgot it again. We're close though. We're really close. So what we want to do is we don't want to use the oriented thing here. What we want to do is actually we want to make point box equals to, we want to figure out the point, which we can do easily using the half vector, and then rotate it. And that's what we did. That's what I did wrong. So that's what I'm going to do here. And instead of the MV oriented, I'm simply going to use the half width for all of these. There's probably a faster way to do this. For those of you watching at home, fast forward. Cool. So what am I doing here? I'm taking the center, I'm calculating the point of the box that I want, and then I'm rotating that point, and then I'm using that point to determine what's the maximum and the minimum point of my new box. You can kind of see now. Look at that. The points, the box is transforming in response to the underlying stuff. Now if I move it, oops, it doesn't move. So there's 2 options here. You can do this in global space, or you can do it, you can translate the box and calculate it otherwise. Now this is a little bit hard because what you want is you would want to translate it only by the by your center, but also by the position of your underlying object. So my recommendation, just to make math easier, is to do it everything in world space at this point. And the way that you would do that is instead of doing it here, you would also multiply your point box, and you'd get the get center global, not the actual, not the other thing. And this will be a little bit better because your center is now going to, well, we need a couple to fix a few other things, but it'll hopefully move around with your thing. So how do we do this correctly? Well, we want to first use the MV center G. Now we're creating the up, down, left, right, etc. We also probably want to rename. Oh, we also probably want to change this because this is we're using this in up here as well. We also want to rename this to G because these are all going to be global values. Making sure that everything we do here is correct. or half width is still going to be local. There's no such thing as a global half vector. It's just going to be reoriented. And our new MV center RG, this is the part we need to sort of not do. We were doing before. We have to sort of just set it to our we don't need to do that at all. And that's more of a convenience value at this point. Let's see if we broke anything. Oh, another thing we need to do, well, again, we're running into this M4 2 world times point box. We just want the rotation. Well, we're getting that. We're only doing the rotation here. So this should work. It looks okay. It looks like it's working. And now when we move it, it should move together. And if we do this in this space, you'll notice there are cases where things don't line up perfectly from orthographic projection, like you're going to have like extra spaces in some dimensions. That's because you're only looking at 2 dimensions and you might have sort of a hidden thing somewhere. But yeah, looks good to me. So now let's go back and get things back to normal like we had. Let's get our Steve stuff going on, and let's do that, and let's do the collision checking again, and let's get rid of this weird thing and then bring Steve and friends back. So first, let's make sure that nothing broke. And now we only collide when the oriented bounding box is working. Whoa! That looks like a bug to me. I'm not sure about you guys, but that seems wrong. Okay. What else is wrong? What else did I do that is incorrect? Oh, I guess I should actually keep it this way. Great. This is a bug I remember from a long time ago. Let's see that this still works correctly. Okay, great. Now the issue is why... I think that's a specific, like a 0 thing. I'm not going to track that down because it doesn't, it only occurs in a particular dimension. Oh, no, here we go. There it is. So it's happening in Y. So something is wrong about our Y calculation. I'm gonna pause while I figure this out. Another bug. Tasty. Okay, so this is a bit of a funky one. The fix here was a little bit funny. So again, this kind of comes down to how you calculate your reoriented bounding box. You don't actually need to put the center of the box at 0. You don't need to really do anything to it at the center of the thing. You just start at 0, and then you create a box from that point. Then you reorient that based on this mat 4 world. Ultimately, you're going to position it where it's supposed to be. You're going to calculate the min-max, and that solves the problem. you just get rid of all of those little small things which were just getting added and adding non-linearity to it. So now you can see that we're contained, everything looks good, there's no bugs. Woohoo! Great. So now, let's go back to our tests. If we move over, before we had bounding volume tests, and so we still haven't added this bit, right? We want to be able to check the outer bounding volume as well. Is that what we're already doing? I don't remember implementing that code. So there we go. Yeah, I don't know why that was causing a collision earlier, but it shouldn't have. So now what we want to do is we want to use these new bounding volume, this new bounding volume, the external one, to determine a collision instead of the underlying one. And the way we do that is we go down to the collision code, is colliding. And actually, you know, this is we don't want to check the other one as a pre-check. We want to check the new oriented one. So let me just get rid of this code, or just comment it out, because we're just going to copy it. I just want to have it available. And instead of the G, we just use the reoriented values that we calculated in update. And I think that this is sort of indicative of the big difference between the reoriented version and the oriented, in that when you're reorienting every single frame, you're doing all of that math. You're well, really you're doing that every time you change the model matrix. So it's not every single frame, at least, but it's still pretty often. So if you're doing some like physics engine, you're going to be doing this all the time. And now you can see the code should, okay. That shouldn't happen. Okay. Well, before I kind of pause and figure out the issue here, as you can see, the stuff gets a lot of trip ups. The point I was just trying to make is that when you're trying to do this stuff, you know, you are going to be doing a fair bit more math. In this case, it's being done in the set model matrix call, which currently is being called every single frame. But you can imagine you don't need to do that every single frame if you don't want to. So let me kind of debug what's going on here, because there's something else kind of lurking per usual. All right, so this was introduced because of the fact that I removed all the locality from this before. So all I have to do is kind of update the max and min with the global center here, so that we can actually calculate it against its actual position. And the way we're going to do that is we're going to go mv3 max LRG. Or are we doing the G down below? Oh, maybe that's another reason. Oh, we don't want LRG. We want no L. Or we want L and G. We don't want, there we go. So this is going to be all wrong. So we're going to, this is local, of course. And then our global is going to be our local plus our MV3 center G and same thing for min. And hopefully we can use that here in GR and LR. So before everything was set to 0, that's why we didn't see any real behavior that we expected. So let's LRG is undefined. Great. So first of all, let me make sure that our thing is not broken again. No nonlinearities are introduced by moving it around. Great. And now let's see that our collision bounds is being checked like before. Cool. So this is working again. And now you'll notice, hopefully if this is working, now when the reoriented bounding box touches, it'll collide as well. And this is sort of a good example. If we look closely here, we can sort of see that in this case, the reoriented bounding boxes are touching, but the oriented bounding boxes are not, or wouldn't be if it was straight up. So you have a slightly better collision detection in this case. It's more accurate, it's less error. Might not seem that way because we drew this yellow box, which is the oriented bounding box, and we want to be able to have the oriented bounding boxes colliding, and then we have the least error. But that requires a lot more testing and a lot more checking. Very similar to what we were doing actually with the realigned bounding boxes, but different. And so, no, this was kind of a long one. This is probably one of the hardest things to get right, is to get all of these points checking in the right way, in the right order, making sure that you're taking locality into consideration if you're in world space or in local space, and then making sure everything is rendered correctly. But you can see here, this is actually a pretty good algorithm, and even though it might be a lengthy lecture to kind of run through, has been done in a relatively short amount of time, given just a few hours. So great. If you guys have any questions about this lecture, please bring it up in office hours, bring it up in Discord. This is one of my favorite subjects. I love working on this kind of code. One of the engines that I've written actually does this sort of nested, so you can imagine bounding boxes and bounding boxes and bounding boxes and orient, and you can switch between them, and it's really, really cool. And getting all that stuff to work was a nightmare, but it was really effective. You can create extremely complicated hierarchies using these things. So yeah, that's about it. Thanks for watching.